Hello and welcome back to part 2 of Make Your Own Emulator. In this part we will make the chip threaded in 2 threads, one for updating the actual chip and one to keep the frame steady and drawing. And we'll start loading the program into the memory and we'll code the first couple of operation codes. So let's get started. We'll begin with making the chip threaded, because we will need some extra thread so we can draw and update simultaneously properly. It's not really needed to do all the hassle because our systems are strong enough to process everything. So first of all, I will just export all the coding from the main to the class called main, so it can be properly done. So in this setup we can nicely code everything in an object-oriented manner. So right now it thinks it's not utilized, so we'll create a new main. That's basically everything we need to do. So we'll I will also store it. And call main.start. So we'll extend main from thread, extend from thread. So we'll add the function called run. The run method is the basic loop of a thread. So I will also write this piece down, load program, which I will use Pong as a reference. We'll create this function later on in this episode. So we know the chip 8 emulator runs at 60 Hz, which means 60 FPS, or updates per second. So we will loop it until the program gets closed. And in that loop we will need to execute the chip 8. Then if we need to redraw the screen, we will redraw our frame and remove the flag. And then we will sleep 16 milliseconds, which comes in at about 60 updates per second. It will be just a bit slower as we actually need 16.666 or 333, something like that. I can't really emulate it all that properly, or I should use vsync, but that's totally out of scope. So we will add these two functions in our chip, and we'll start coding them. So to check if we need a redraw, we will use a simple boolean for that. So private boolean need redraw. By default, need redraw equals false. So in the need redraw function, we'll just return the need redraw variable, and in remove draw flag we'll reset it to false. Now our chip or the frame will only get updated if there has been a change. For now it doesn't matter all that much because our system can handle it fairly easy, but back then it was quite a problem. By default we need to catch the interrupted exception, but because we will not update or interrupt the other threads, it will never ever get thrown. So I'm not going to handle it at all. So that is also basically the entire loop for the multi-threading. So to continue, we will start loading the program into the memory. So the string is actually the file name. We will use a data input stream to read every single byte from the file. Data input stream, new file, input stream, new file. This will possibly throw EO exceptions, so we will need to catch those, and I will print those to the screen and then exit the program or exit the entire application. I'll fix the imports by pressing Control Shift O, and this will shoot data input stream, not data input stream. Alright, so if the file is loaded, we will need to process all the bytes into the chip 8 memory. We can use two constructions for this. We can use for integer offset while loop as long as there are more than 0 bytes available and increase the offset. But I don't really like this because if I use a for loop, I want this variable in the condition section. So I will use the while loop counterpart. And yes, each and every for loop can be rewritten as each other, but it's mainly preference of the coder on what he prefers, or she. So yeah, the program is always starting at x200 or hexadecimal 200, which is 2 times 16 times 16 or so. It's a lot. Big number. I don't care. Big number. So we will always start the memory hexadecimal 200 plus our offset to be equal to the input dot read byte, as we are reading bytes. We will need to cast that into a char so we can actually store it. And this is basically the entire loading process. And of course it does want us to close the file as we have a resource leak. But that's a matter for soon. This coding will actually result in invalid memory data in our memory, because the byte is casted into a char. It's just covering up the negative value, but it remains negative if the byte was negative. I got a demo for that, which basically as the first 2 bytes of the program pong in a little memory section, and by this cast you can already see that something fishy is going on. because this is basically between or 265 possibilities. But yet Java says, no, I can't store that in a byte. So to see what happens, I will cast the first byte, which is hexadecimal 22, which is a positive number. Then I will display the hexadecimal FC, which is negative, because as far I know, Java uses the leftmost bit to represent the sign value. Then I will try to cast it to an integer to see if that will resolve it, and then I will use a bitwise operation to try to solve it. So the results are pretty simple. 22 is read correctly from the memory as it's positive and nothing happens. But now we got our FC and something fishy went on, because our FC suddenly became FF, 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 FC. That's not what we want, because if we store this, these two will be stored and not these two. So by casting it to an integer, it's resulting in the same thing as it's just casting, it's just covering it up. But now we will use a calculation on it, which will cast it to an integer, which can store higher values than 127, and that will resolve our problem. So we only say we will bitwise AND it from the FFFFFFC with this. So we only we end up leaving with the last 2 bytes, or the last byte, and that's exactly what we want. So to give me back my space. So to fix that in this piece of code, we will need to add some brackets around it, and we will end it with 256. And this is our full loading code. But I want to avoid this warning, so I will copy this piece of code out of the try catch and say it will always be 0 on by default. Here we'll reassign some stuff. In the finally block of the try catch, I will check if the input has actually been assigned. If it has been, I will close it, and unfortunately that can result into another EO exception, and I will also have to catch that, but I won't handle anything of that, because if it happens, I can't do anything about it, because if I will recall close again, it probably comes out to the same. So this is everything. This will also has removed the warning, as we will try to close it. Alright, so this should allow us to run the program. We'll see. This goes right. Perfectly right. I have already filled in the blank spots here, so I didn't have to look everything up on the wiki. So the first code is 22FC, which is operation 2, which is call subroutine at address NNN, which is 2FC. So to extract the address of from the opcode, we will use a bitwise ending, just like here, but instead of the first nibble, we will store the last 3 nibbles. So the address equals to opcode and hexadecimal O, which is important to add 0. Well, actually no, it's important to add it because we are always using those 4 nibbles, and to keep consistency we will add it everywhere. So I will instantly cast this back to a char because it's nothing bigger than a char. So because this says call subroutine, we need to use the stack to store our current position and then go to the position which is in the address. So it basically is, it actually executes two codes. We could use store stack and then 1 to fc, which will jump to the address. But we are not going to be that sneaky, so we will do it properly. So we will add to the stack at the current stack pointer our current address, which is BC. And to avoid overriding, we will increment the stack pointer. You could also do the increment in here, but it just looks a bit more backed and you will have to take a bit longer look to understand the coding, so I will avoid that for now. So the last thing we need to do in this code is to jump to the address given by the subroutine, and then we got our entire operation code completed. So this is our first operation. Aren't you excited? So if we now see 22 FC 26 6B20, which is an unsupported code, and I'm sad about that because I thought I had all the code stored. Okay. Alright. By the way, if you're wondering where I got the programs are available on GitHub, so you can download them from there. I will have a quick look at the Pong file at where we jumped, because we jumped to 2FC, which is FC relatively. It should be somewhere here, I think. Which is 6B20. Wow, that's far. Yeah, it's correct there. So we can actually see that it jumped all the way over there. Didn't expect that. But alright. Oh yeah, I now get how to read it. FC. Alright, I learned something today. So we will implement operation code 6, which is 6 x and n. I had to look on the wiki page right there, which will set vx to nn. So v is referring to the memory or registries, which we got here. X is the index of the registry, and nn is the value to which we will set it. So we will first get our offset or index, which is at the third spot. So our opcode and end it with OFOO, second spot. And this will be our index in the registry. So our vx will become index. So that's a bit confusing. So we'll just rename it to x. Yes, I don't care. So the assignment to vx has to be NN, which is the last two nibbles of the operation. So we will end the operation code with hexadecimal 00FF. And of course we will need to cast that to a char, because it will by default result in a 32-bit integer. And this is the entire operation. But this is not it, because we also want to advance in the program by 2 bytes, as we use 2 bytes to make one operation code. So we advance the program counter by 2. Or if you want to be really hexadecimal, bum. But I won't do that for now, because I prefer it in this manner. So our next code is, oh, exception. That's not good. B equals 11. I will remove the integer and cast it to a byte, because I'm thinking something goes wrong. And just to be sure, I will print variable x, which is 0, which is not good. Alright, we will fix that by right shifting by 2 positions to get it right here. And then I'm curious, out.println x, and we need to ending first, and then we will shift the operation. So what the heck? 3 positions? I am highly confused. I will grab my old code from the chip 8, which is not correct, so you can't copy too much from that. And we'll also remove it so nobody can see it. Oh, I feel like such an idiot. We don't need to shift it 2 positions, because these are 4 positions, and this is another 4 positions, so we need to shift it 8 positions. And if we will output it right now, it will be x plus x. It should be 11. Yeah, there we go. Oh, I feel like such an idiot now. So, if you wonder why I add the brackets, it's because if I would remove it, the shifting will be applied before the ending, and then we will get the end part, which is not what we want at all. So the next code is A2 F6. So we will add the code OXA000, which is let me have a look. I think I removed too much. NNN sets the address pointer to NNNN. So I added quite some code, but I decided I was gonna do less, and apparently I removed the wrong codes from the example. So probably a couple of these codes won't be handled. So the first thing we need to get is the address from the opcode, which is yet again just like in a stack. So we'll actually copy that, or in code 2 we will fetch duplicate. Why? I can't, I can't access that, right? I will just skip it. I'll just instantly assign the address pointer to the file address, and I will also revise this piece of code to just do the exact same thing, so we won't get as much duplicates errors as we currently get. I won't recode this because it looks really ugly if I do. I can show you. No, I can't. I already closed the file, so I can't show you an example. But I did this in my first attempt, and it looks really awful. So I'm not going to do it. All I have to do with the duplicates error. So, alright. We assign it, and as with almost all codes, we do want to advance by 2 bytes. So the next byte is D. Actually, I don't want to cover D right now. I will add it quickly and skip it. Drawing will be handled in the next episode, or episode part. I will write it down for a second because it will draw a sprite from at XY with size 8 width by n height, and the sprite is located at the address pointer, but we won't handle it right now because it's pretty complex code, and I probably will reserve an entire episode just for that code. Oh. Because who's oh, we don't care about that. So I will skip that code and we'll do the next. Oh, bloody hell! The next code is 7, which is add vx to nn. No, we add nn to vx. That makes a lot more sense. So to extract x, we have basically the same code as with operations. Why is that? As with operation 6, and because of that I will also call it the same or use the same method. So vx equals vx plus I will extract a bit of data from the address. Plus, actually, I will do this in double loops. Add it with nn, and I will re-end that because it might overflow or even borrow. No, not borrow, overflow. And there is a flag for that. which is the 16th flag in the registry, but this operation will not include the addition of overflowing, so we won't add that. So this will be the rest, or concluding the episode, and as the assignment you will load the font set into the memory. I will give you the font set, so you won't have to do it all by yourself. This is the font set. It will be located at the memory position hexadecimal 50, and you guys will have to implement that in the same way as the loading of the program, but you won't need to use a data input stream. You can just read it from this file and get it into the memory. This file is available on GitHub, and I will upload the solution to this on Sunday. So until then.